are, part 2 of Mariana. So today's lecture, I planned it with the idea to first show you some of those applications where distributional equations come from. Yesterday when I started, I gave you some very classical, very basic examples. I believe Cecile today gave us one more, or will end up giving us one other example. And hers, I believe, is a branching recursion, so that's a really nice different example that I don't have here. But I'm going to tell you about some of the examples that motivated my work in particular, which to this day I still find rather interesting and with lots of interesting future potential avenues to explore. So again, taken from yesterday, what we're going to do is we're going to look at those attracting endogenous solutions of certain branching distributional fixed point equations. And I'm going to give you 2 examples in particular where these equations appear in the form that I sort of explained yesterday. The first example is going to be an example from, let's say, from computer science, and it's the analysis of algorithms, in particular 2 of them. One algorithm known as Quicksort, and one algorithm called PageRank. PageRank, if you have heard of it, PageRank is, at least in principle, the algorithm that started Google as a company, as the web search engine. You know, back in the day, some of you are probably too young to remember, but there was a time when we had like 1 billion different search engines. And at some point, one in particular became more useful or more popular than others. And that's the only one we really have to this date. At the very beginning, Google, which was started by a couple of college dropouts from Stanford, was based on a very, very simple idea, which you will hopefully find very interesting when I explain. The second problem is a motivating example for the higher order Lindley equation, where you see that it's a queuing problem, but it's a queuing problem that rather than give rise to that simple Lindley equation that I showed you yesterday, it gives rise to the branching version of that because we have many possible avenues to go to. And that comes from a problem related to queues where jobs have to be split into pieces and then processed simultaneously or in a synchronized fashion. And that's sort of the motivating example. So I said before, what I'm going to be studying is the attracting endogenous solution to those fixed point equations. And as I said yesterday, with very few exceptions, the one that Andrea solved for you guys yesterday, and another one, the one that Cecile will solve or basically hinted at today, there's very few examples where you actually have explicit solutions. So rather than looking at the exact solutions, I'm going to show you other ways of trying to get meaningful information out of those. As I said yesterday, in great generality, the naive approach of just simulating the tree and trying to compute recursively the fixed point equation from the leaves up to the root is not very tractable, especially when you have very high mean number of offspring on your Galton-Watson. And therefore, what I want to talk about mostly after the examples today will be an algorithm, a simulation, a Monte Carlo simulation algorithm that allows us to do that very efficiently. And hopefully, you'll find it interesting from the point of view of the mathematics behind it, and also because it is basically the standard way of computing many things, and it's interesting enough that nobody has really analyzed it, so there's still some open questions in there as well. Let me start with PageRank. As I said, PageRank is that algorithm that basically allowed Google to rank every website in the World Wide Web. And you would think, well, that sounds rather complicated, but the idea was very, very simple in the sense that Google totally ignored the content of the web pages. So that ranking that you see, at least in principle, has nothing to do with what the page has. And instead said, well, let's write a number. Let's give each website a number, a universal number that doesn't depend on anything else. It's a rank. It's a rank in the sense that it's a number between 0 and 1, where numbers close to 1 mean that the page is more relevant to some sense. Once you actually do a keyword search on your web browser for, let's say, CIMAT, I'm pretty sure there's going to be hundreds, if not thousands, of pages that have the word CIMAT in it. The thing is, most of us will only look at the first handful of results. So you really want to be at the top, right? And a good search engine is that is going to allow you to put the most relevant, most interesting ones at the front in the first page or second page, right? That's the idea. This universal number is called the PageRank. And the way that it was designed to work is basically by solving a very large system of linear equations. Now we're talking about a graph, the web graph, where the nodes on the graph are the web pages, and the arcs are the links. Links, as you guys know, are directed. So we have outbound links from one page to another, and inbound links, those that bring other pages to that one, right? So we have an underlying directed graph with n vertices, and I'm going to solve a system of linear equations that basically says that the rank or page rank of page I is going to be something we call the personalization value. These Q's usually are a probability distribution function. I'll explain that in a minute. Of a weighted, these are weights, 1 over DJs, the ranks of the neighbors. The sum is taken over all the neighbors pointing to that particular web page I. What are these weights? This DJ in the most standard form of PageRank is basically what we call the out degree. It's the number of pages pointing out. So in some ways, what the idea behind PageRank was, let's sort of take a weighted average of the neighbors and penalize those pages so you don't get that much of a contribution if that page that is pointing to you is also pointing to lots of other pages. On the other hand, if that page that is pointing to you is very important and it is going to be very selective about where to put outbound links to, then you got a lot of benefit from having that page be important. I would say, like, if you manage to have a pointer from the Presidency of the United States web page to your web page, trust me, you will be starting to go up very, very fast. Even better, get one from Kim Kardashian's personal web page. So the idea is, this is a system, this is just a system of linear equations, and it's roughly in the tens of billions at this point. So it's a very, very large graph. It's a sparse graph. The number of arcs is of the same order of magnitude as the number of nodes or the number of vertices. And the idea is you're going to solve this. And once you solve it, you have these ranks. In practice, of course, this is a moving target. Every second, the graph, the underlying web graph is changing. So, you know, it's not quite as trivial as I make it sound, but the idea is assuming that you can solve it, you're going to end up with a vector of the RIs, right? That's the PageRank. Now, that's something in general hard to compute. It's done in principle, what it's called, sort of using little programs called web crawlers that are constantly updating. They're jumping from one place to another and updating locally as they go around those PageRanks. Every website has a hidden place where you can actually see what your PageRank is, so that when a web browser comes in, uses that number to determine in which order it comes up in case that web page is selected within a keyword search. Okay? Now, if I think about the original PageRank, I make this QI equal to 1 over n. As I said, a probability vector function. Is not that hard to see that if, again, these are just going to make them a constant. That's the original PageRank formulation. What I really have here is a random walk. These are the system of linear equations satisfied by the stationary distribution of a random walk on the very, very large web graph. Which random walk? Well, it's a random walk that is famous on its own. It's called the random surfer random walk. And it says the following. Remember, let's ignore what the web pages have. So if I ignore the content of the web page, basically what I'm going to design is the simplest random walk that I can think of, which is if I'm page I and there's 17 outbound links, I'm going to pick with equal probability one of those 17s and go there. Once I get there, if there's 3 links out, I'm going to pick with equal probability one of the 3 and go there. That's basically what I would do. The only problem with that is that every once in a while I'll get stuck. As a matter of fact, you'll get stuck rather often. You'll get stuck every time you reach a web page that does not have any outbound links. In that case, what you do is you sort of fix it in a random fashion by adding to these random walk an unstucking mechanism, which is the best way that a probabilist would get unstuck of any situation. You toss a coin. So what do? You're going to toss a coin that, in case you get stuck, you're just going to pick, in the simplest form, equally likely not among the outbound links, which may not be any, but among every single web page in the world. So that's sort of the unstuck mechanism. If you're going to get fancy, instead of making that unstuck mechanism to be 1 over n for all the web pages, make it some other personalization, vector that you might choose. What I'm going to do to this equation, everything here, if you think about it for a few minutes, as long as I'm not talking about a very weird graph, the r's are going to be of order 1 over n. Again, with n in the tens of billions. So it's a pretty large number. So rather than work with those, multiply everything by n. And it turns out, because of this sort of sparseness of the graph, that if I multiply everything by n, and if these guys are of order 1 over n, then these guys actually are now neither 0 nor blowing up. Right? They're approximately something that is of order 1. And our goal is to study those scale-free ranks that I'm going to call Ri. Right. So the idea of getting to the branching equation is sort of as follows. And for that, I'm going to use a little drawing over here. Let's say that I have a vertex with incoming ones, outgoing, incoming, and then from here, out, 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 from here, out, out, maybe from here only one out, then again here from other places, and so forth. What we're going to do is we're going to say, well, if I take randomly one point here, I want to compute that system of linear equations. But that system of linear equations, basically it's a system of linear equations of the form a vector r equals a matrix M times a vector r plus a vector q. I promise to go more into detail later. This is sort of just a quick introduction about this principle, which means that I can solve for r. Let me transpose everything. Right. So now I have, for whatever reason, in computer science, usually think about r as a row vector. So this is the row vector notation. I'm multiplying on the left. And if that is the case, then as we all know, as I was explaining yesterday, that means that these guys are going to have to be converging to 0 geometrically fast for this to be finite. And if they're converging to 0 geometrically fast, I may as well chop off the end, right? And if I chop off the end, that means that whatever it is that I'm looking, R is determined only by looking at the first, let's say, k neighborhoods of my node. But my small k neighborhood in many graphs is going to look like what I drew here, like a tree. That's the main idea behind these things, that as long as we take a random graph model underneath that has enough structure to give us this local tree structure, local neighborhoods, tree-like neighborhoods with no loops, no cycles, then what I expect to see is that if I look at the system of linear equations, basically all I need to do is look at the local neighborhood that looks like a tree. Yes?
Is it reasonable to assume it's tree-like? I mean, because typically pages self-refer, right?
It is absolutely true that it is unrealistic in the real world. Of all the stuff that has been written for random graph theory, give me a model and chances are it does have a local tree-like structure. So again, from a mathematician's point of view, all the random graph models are mostly locally tree-like, at least the original ones, including the very famous Hurdle's-Rennie graph. The one that I have here is sort of a version of an Erdős-Renyi that's a little bit more inhomogeneous than an Erdős-Renyi graph.
Can I extend my question?
Sure.
So, I mean, is there kind of a level of scale here where if you kind of group pages together and think of them as one page, then it's maybe that?
Well, again, I think you're going into even the more nitty-gritty of take a real graph and see what is a good model. And I think there are models that do exactly that. For example, there are models that take a local tree-like model, like a configuration graph or an inhomogeneous graph at its core, and then puts little sort of what they call household, more connected graphs there.
Yeah.
There is such a thing. Whether that is really a much better depiction of a real network or not, that's still something very debatable, right? So yeah, that's a complicated question. One thing that I will say, which is rather surprising, and it is very surprising, is that a lot of these analysis, let's assume that you bite the bullet and you just say, yeah, I'm going to believe that my real graph is locally tree-like. You do the calculations, you get your predictions. And for whatever reason, all those triangles that are there and all those dependencies, in some cases, don't seem to be affecting the predictions. And I did this experiment. I was surprised myself. I had a student do it for a Wikipedia webpage database. Wikipedia it's a directed graph, and it's pretty large. And he did it like on 4 different languages. And in English, which was one of the best, and we can talk about it. It's really fun to think about what the differences between languages are. The fit was very good. However, I'm pretty good. If you open right now a Wikipedia page, I'll get you a triangle in 3 seconds. So why? That's still an interesting and an open question. Why is it that it seems to be robust? I have my ideas. We can talk about those later. Okay. However, Dutch doesn't work. No, Dutch it's a little bit off. Anyways, at the end of the story, what happens is that if I look at the local neighborhood, what I end up getting is, and I will go into the details tomorrow. What I end up getting is that basically look at this neighborhood from here. I look at contributions of these neighbors. Those look at the contributions of these neighbors and so forth. What I get is basically, at least in a heuristic sense, a non-homogeneous smoothing transform. Just look at the previous slide here. I have R on the left. Think about that, your randomly chosen node. And then this is a Q that goes with that randomly chosen node. And then this is the sum over all the neighbors. But if all the neighbors, if I ignore the fact that this is a graph and just replace the neighbors by a random number of neighbors, then I get my n from yesterday here. And then I get some coefficients that multiply the r's. And because, in some kind of limit sense, everybody should have the same distribution, there you go. There's a lot of work that goes into what I just explained. And I will spend more time making that argument rigorous, because until very recently, there was no rigorous proof of what I just said. So this is sort of a big thing. But heuristically, it sort of makes sense that as long as you have a graph where the neighborhoods are fairly tree-like for long enough, these heuristics should work. As a matter of fact, I'm going to tell you, it does work for a variety of family of random graph models. And what we proved is that the rank of a randomly chosen node, as the number of nodes goes to infinity, and trust me, even a small graph of 1,000 nodes is big enough already to see this happen. The web graph, we're talking about tens of billions, so you can imagine that's pretty much infinity. Then it will satisfy this sort of representation. This is the most regular general representation for graphs where you have lots of dependencies between in and out, and it's rather the most elaborate case of it, where the rank of a randomly chosen node can be written in terms of a linear combination of some random variables as xj's, where xj's satisfy the smoothing equation. This one in particular. So again, this is rather a lot of work, but the idea is as long as you have local tree structure, this trick that I just explained works for PageRank, but it works for many other things as well. In principle, it also works for a lot of these sort of belief propagation algorithms, as long as you have a sparse enough graph underneath, and your map that you're trying to compute is converging fast enough so that you only need the first few steps to get most of whatever is happening there. Now let me quickly tell you another model of where the maximum, the high order Lindley equation appears. This is a network of, let's say, computers, if you think, or servers, or it could be even files within a computer. It could be a variety of things. Let's think about computers. And I have a very large number of computers, let's call it n, and they're all working in parallel. Think about it as a server farm. Jobs arrive to the network according to a Poisson process to keep everything simple. And when they arrive, they are split into many little pieces. Right? Depending, very large jobs will probably have more pieces, small jobs will have fewer pieces. And then those pieces will be shipped out to specific servers in my network. And the condition is that they're going to have to be processed at those specific servers, but they have to be processed at the same time. Again, think about a program that is requiring access to many different files. And because it has writing privileges on those files, while it's working on those, it's blocking any other program from doing anything to those files because they're potentially changing. So it's blocking a whole bunch of files until they're done processing, and then they can keep going. In the meantime, other programs may request some of those files as well. And if they get there and they find that there's other jobs in front of it, they will have to wait. So there's a lot of blocking and inefficiency that happens in this kind of system. And we're assuming that everything comes and is served in the order in which they arrive. So my pieces are going to be shipped out, and they're going to join a queue to be served in a first-come, first-served basis. And I said the big thing here is that we require that everybody gets synchronized. This is the standard picture for the model. You have Poisson processes going in here. This is my job. My job here, the pink job, has 5 pieces. The job in front of it is this black job that had 3 pieces. Those pieces are going to be routed to specific servers, either because you are randomly routing them or because you can assume that if you have no information of which files they're required, you may assume that they're uniformly distributed throughout all the set of files that you have. So they're going to be randomly just choose out of the n, choose the number of pieces that you need, and they're going to be shipped out. Once they're at the servers, they will join a queue. So for example, here I can see that this piece of a red job, when it arrived, it found the server empty. This one, on the other hand, when it arrived, had 2 jobs in front of it. Notice that the red job is stuck because it cannot begin its service until this other red job over here makes it to the front of the queue. So these red jobs will stay there, and if other jobs start piling up here, in particular this black one, the black one will be stuck until at least the orange and the light blue one are done. You see the idea?
Isn't this a bit-torrent model?
Sorry?
Bit-torrent model.
Bit-torrent model?
Yeah.
I have no idea. I'll be happy to look into that.
Back in the day, when movies were illegally distributed around the internet by breaking them into bits, and you could download software where you could access these movies, but the price to pay for it was that you became a server for somebody else. So, and you couldn't be caught because the movie was split into millions of bits, and then somehow it was all processed and reassembled across whoever was online at the time.
So yeah, I guess that sounds about right. So this is that model. Again, here, the number of pieces is random, so you can see where my n is going to come from. And when I ship them out, I have sort of this queuing mechanism that that is going on in terms of all the queues at different places. what I'm looking at in this case is basically the stationary version of a queue. So the waiting time prior to starting service of a job that arrives into the system in stationarity. So of course, let's assume that that this system will be stable under certain type of conditions, and I'm telling you, yes, it will be stable. There is a stability condition. And once we satisfy the conditions for stability, then we're looking at the stationary waiting time of a job. So basically what I'm looking is, I'm going to tag one job in the standard Lorenz construction and send my initial empty time to -infinity and look at that first job that arrives at time 0. And I'm going to say, well, how long did it have to wait until all its pieces made it to the front of their queue so that they can begin service? What we have there, again, in the pre-limit, this is not a Lindley equation. This is not a higher-order Lindley equation. And the reason for that is because there's a lot of dependencies. And you can have sort of crashes in between pieces. For example, 2 pieces of the blue job could be behind 2 different pieces of the pink job. And that creates a lot of dependencies and complicated things. So it's not quite exactly, the model itself does not satisfy a Lindley equation, just as PageRank does not satisfy the smoothing transform. But the whole thing is that in the right limit sense, you can prove that the limiting object will satisfy a high-order Lindley equation. And again, because the way these things work, the convergence is so fast that this limit is actually a pretty good depiction for any finite system as long as n is big enough. So in that sense, it's actually very, very close to what you really want to compute. So these are 2 setups where the higher Lindley equation and the smoothing transform pop up. I will go in the next 3 lectures a little bit more deeply into the PageRank case just because it has very interesting connection with a variety of random graph models. And if you guys have never seen a random graphs, I'd like to elaborate more about what are the random graphs that work and how exactly this coupling that we do between the graph and the branching process, the way the branching process occurs, so that we can actually argue rigorously that these are the limits in both cases. Let's go back to the computational aspects because that will give me a chance to actually give you some open questions that I think are interesting and worth publishing and not that hard to solve. So let's go back to these 2 solutions that I mentioned yesterday. We have the smoothing transform over here, and we have the higher-order Lindley equation here in its multiplicative form, right? And I already argued yesterday that the attracting endogenous solutions to both of these are the sum of all the weights over the entire tree for the non-homogeneous smoothing transform, and the all-time maximum over the tree of the weights for the higher-order Lindley equation, right? So what I said yesterday is that in general, if I think about R as the solution to a map phi, whatever phi is, in that case either the smoothing transform or the maximum equation, then I can always think about looking at this from the finite tree perspective. I run my tree for a large number of generations, let's say j, and then I can think of it as starting with the leaves and computing the map at the leaves, then use that to compute a smaller set at the second level, j minus 1, then use those to compute a smaller level at j minus 2, all the way until I get to the very top of the root of the tree, in which case I should have something fairly close to what I'm looking for. Yesterday I also mentioned that we could use sort of a measure notation, and this mu k is the probability measure of looking at the PageRank computed, let's say, up to a tree of depth k. As I said, if k is big enough, everything works out. And mu is the actual fixed point. So yesterday I wrote that mu k is equal to t of mu k minus 1. And of course, we're looking as k goes to infinity to the fixed point, which is this mu over here.
So, computably speaking, it's very, in terms of time.
Think about this.
Convergence is very expensive.
Oh, absolutely. Think about your binary tree. Let's say, I'll tell you in my experience, usually 10 generations are enough for a good enough contraction. So let's say I want to do 10 generations on a binary tree. How many are you talking about? That's 2 to the 10 copies of the branching vector, right? Whatever effort goes into that for one observation. Now, if you want to use a strong law of large numbers for that, what do you want, 1,000? I would never trust a simulation that doesn't have at least 1,000. And if it has very poor moments and finite and infinite variance, then I wouldn't even trust 1,000. Trust me. So yes, we're talking about a geometric complexity. In practice, some of the examples that I work with, the first time my student brought me this problem, he has like 2 weeks worth of computational time. That was about 5 years ago on a fairly good personal computer. I think Arnaud was saying also a couple of weeks for his, which was also a binary tree, only 2. So yeah.
And is someone, in some sense, looking at this type of problems for like some mixing times or something like this? I mean, for all this convergence, in order to find like a right amount of
well, this
recursions that you will need.
well,
To be very close to the.
yes, this is this line over here, right? Because usually what happens in practice, and I think Arnaud also mentioned a little bit about that, was that many times the map itself defines a contraction, if you're lucky, under some metric. Sometimes the metric under which it has a contraction is not that obvious. For example, Quicksort satisfies a contraction in the Wasserstein metric of order 2, but not 1. PageRank usually satisfies it for the Wasserstein metric of order 1.
So this is like exponential ergodicity in some sense.
Yes.
Right? Okay.
So the idea is that the first step is, and this comes more from the analysis of the solutions rather than the original problem, you usually will argue, just for the existence of a solution, you will argue that there is a metric under which this map defines a contraction, so that you can construct that explicit solution. So again, which metric is sort of depending a lot on the specific example. Once you have this, you have a geometric rate of convergence, you have a strict contraction, so you can easily see that it's not, you only need, if C is 1/2, you know, you only need only a few steps, right? Yes. To get to have a really good accuracy. So that means that, as I said, in practice, K could be 9 or 10. Usually at that point, we see a very good convergence already. So let's say that I want to compute R10. Of course, in the PageRank case, the average number of in degree in the web page is 33. So 33 to the 10 for one observation doesn't quite work. So what I started saying yesterday is, let's go the simulation approach and use that geometric ergodicity to say, well, because it's converging so quickly, geometrically fast, then I don't really need to take a look at all the tree. I'm happy with only a few generations. And because with only a few generations, these are the quantities that I want, well, you know, in principle, let's just compute the trees and do that. We talked about that yesterday. That doesn't work. Or I said 33 to the 10 times 1,000 doesn't really work. This is the algorithm that I found hidden in the literature in a variety of places. We discovered it on our own, like many times. I guess it's not that hard to come by if you think about what to make it efficient. When my student the first time, his name is Ning Yuan, and he's now a professor in Hong Kong. He said, well, Mariana, this is going to take me 2 weeks of time. I said, I just need a picture. 2 weeks of computer time, are you crazy? And then he was very disappointed. And then about a week later, he came back. I think I've solved the problem, and I figured out how to compute this faster. He came up with basically his own version of this algorithm, which I later found is also buried inside of that survey paper by David Aldous that we were talking about yesterday. And it's also hidden inside this book by Michael Jordan on belief propagation. And the idea is the following, that if you want to do this, let's at least reuse my base. So think about, I'm going to construct that base of my 10th generation of the tree. So I'm going to construct a very big sample on the bottom. But rather than losing 1 over the expected number of offspring each time by getting this into this tree and all the way to the top, let's reuse what I already computed again and again and again. This is something we call bootstrapping, which basically says rather than sampling new balls, let's every time you sample a ball, use the value, put it back, and use it again. As long as you have enough balls then chances are that most of the balls that you sample are not going to be the same, and you're not introducing too much dependency to make everything go wrong, right? That's the basic idea. Well, that's exactly what we're going to do here. Let's take a big sample pool of, let's say, size M. I'm going to call that M. And generate the leaves of my tree, as many as you can, whatever makes numerical sense. You could do 1,000 or 2,000. It doesn't have to be huge. And now, when I'm going to compute my first batch of, to go from level J to level J minus 1, and for that, rather than using whatever, sampling from that pool and tossing away, after I use them, I put them back in. So I'm resampling. And then, with those resamplings, I'm going to construct one more iteration, and I'm going to construct another pool of exactly the same size as I had before. So if I started with an M of 1,000, in the next iteration, I'm going to have another M 1,000. I haven't lost anything. Rather than losing 1 over mu, I haven't lost anything. And then, for the next level, I'm going to do exactly the same thing with the previous pool. So I keep going from the bottom up, but at all points, keeping the pool size constant. Now, what is going on here? What could go wrong? But the standard question, Bootstrap has been a technique that has been out there forever. And mostly we're talking about using it only once. And even then, there's interesting questions about it, which is when you do this, you're losing the independence among your sample. They're no longer independent. I do claim, and this is a first little exercise, that they are identically distributed at all points on the same level. Those they are. Verify that yourself. They are not independent. However, they are conditionally independent given the previous sample set. Okay? So now you have that they're only conditional independence, and the question is, well, yes, because they're not truly independent, then what I'm getting is not really what I should be getting. So I'm introducing some bias in there. So I'm not really iterating the map that I should be iterating. I'm iterating something that is approximately what it should be. So I am losing on two ends. I'm losing on the lack of independence, which in turn, when I use it on the next level, is not giving me quite observations of what I should be getting. So you're losing this, and on top of that, you're doing this many, many times. So the question is, well, if usually one wonders even for simple Bootstrap whether this approach works. You know, here the question was, well, can I make it work not once, but J times on something more complicated? What do you get at the end? Well, you get a pool size of size M, which you can use to construct your distribution function, your empirical distribution function. So this is the empirical distribution function of those final set of pool values that I'm getting, so my final sample, which are identically distributed but not independent, and they're not distributed according to what I would like them to be. However, if everything is good in the world, what you expect is that all that independence and all those things that we've been doing is not messing up things bad enough in such a way that I still have, at least in an approximate sense, something very close to what I originally was looking for. So this guy over here. And to my surprise at that point, after we sort of wrote about it and came up with our own version of this, and then I discovered it buried in the literature, I even asked David once, like, do you even know that this converges? And I'm like, well, it should. Those of you who know him, you know, he just said, like, well, it should, but, you know, never really proved that it does. Which is sort of surprising considering that there's a billion papers on just the Bootstrap. But so I said, well, let's try to see what, because yeah, at least to know. And the other thing that was worrying me quite a bit is we have things that can be very, very heavy tails. I'll talk more about it, but in PageRank case, that thing is poorly behaved. You have infinite variance. You have all sorts of issues. So if you add that to all this bootstrapping, the question is, are we even getting something meaningful? So on that sense, we really wanted to know, and I figured, like, let's see what we can say about these. And we ended up getting to a couple of different conditions under which we could prove interesting things. And again, this sort of reminds me a little of what Arno was saying and those contractions. And these are basically contractions that are, these are well, Lipschitz conditions of different flavors that are going to guarantee that I can find a contraction under one type of metric, at least. This first condition is a Lipschitz condition on the expected value of the difference. Everything is the same, so these guys are the same here, and what I'm changing is I'm taking some x's on the left, some y's on the right, and what I'm saying that is this expected value between the two different maps is smaller or equal than a constant times the expected value between the distribution of the two, so the LP norm on the right. I got rid of the 1 over p's, so it's not a norm, but the same is true if I make it the norm there. The other condition is a little bit stronger because it's a Lipschitz condition, but on the actual path. This is a in-mean Lipschitz condition. This is an actual Lipschitz conditions on the maps. All my examples that I showed you do satisfy Lipschitz conditions. So again, it's not anything hard to satisfy by everything that we've been talking about. Even our NOS yesterday will satisfy this. So all of these maps will satisfy Lipschitz conditions of this form, but this is a little bit stronger. This implies the other one. So I'm going to call those two. And the family of metrics that I find particularly useful and that people in weighted branching process have found useful for many years now is the Wasserstein metric. So the Wasserstein metric is basically the infimum over all couplings of my two distributions f and g. What I mean by couplings there is if I have two distributions functions f and g, I'm going to take one pair constructed on the same probability space whose marginals, the marginal of x is f, the marginal of y is g, but they can be whatever you want in between in terms of their joint distribution. If you choose well enough what those are and you take the infimum over all possible couplings and you compute the norm of that best pair, then that's defined as the Wasserstein metric of order p if I'm using the p norm. What's beautiful about the Wasserstein metric is that it's explicit in the sense that when you're working on the real line, the optimal coupling is the inverse transform or score hot representation of your distribution. And that is the best you can do, which means you take the inverse functions of your two distributions, or generalized inverses if they're not continuous, of course. And then you evaluate them on a uniform between 0 and 1. And that's the best optimal coupling, in which case you have attained the infimum. So
do they use the total variation? Or
people have used it, but this works very well for these purposes, and it's really nice. I find it very useful. And what's nice about this is that it's strong. It's a strong metric in the sense that, you know, I guess we've been listening to everybody talk about the whole martingale convergence for the Galton-Watson. The big question is not whether it converges. The big question has always been whether it converges, whether it's uniformly integrable, right? So this sort of does both at the same time. But convergence in the Wasserstein metric gives you the convergence of this distribution and the convergence of the moments. So in other words, for the optimal coupling, you have LP convergence. And, you know, it's therefore you get the uniform integrability in there too. So so yeah, there are other options, but this one seems to work rather well in practice.
Yeah, I mean, if you have p moments, is good.
Yeah, I mean, in many cases you don't have p. You have one moment, p equals 1. Maybe if you're lucky, you might have 1 plus epsilon. As I said, in the real world, almost any interesting graph that you can give me, I can probably argue that it's going to be very, very heavy-tailed. And once you're there, as you know, you will lose those moments very quickly.
And there is, I mean, on the limiting distribution, there's any some structures that you find relevant?
Limiting distribution of what?
I mean, the kind of, well, the limiting distribution that you are observing in this distance, what's this new that you were computing?
I mean, we know usually we have that C, right? You can explicitly compute the contraction. Mm-hmm. So that tells you how fast it's converging. That usually goes into many of the proofs in that area as well. But
about the mu, you don't know many. I mean, you don't know nothing about the structure.
About the mu k, like the actual endogenous. No, I mean, except for the examples just that the few explicit examples there are, no, we don't have an explicit solution for the endogenous solution, no. But there's very few of those. So that's why you need a numerical approach. So again, I won't go into the details of the proof, at least not right now. But what you can prove under those assumptions, usually this comes for free. This is just sort of a weak way of writing it. But you will get that this is bounded because this is converging in LP. So these moments will be absolutely bound, in which case it doesn't matter if I have this. But even if it doesn't, even if you were for whatever reason, and I think I'm going to argue that that's what David wrote on that paper. He's like, sometimes you use this method to even find out if there are solutions, endogenous solutions. In which case, up front, you don't know if it's even converging. So again, you pick a big enough K, and you hope that these guys are finite. For finite K, maybe it's easier to argue that the expectations are finite. And then you're looking for some pattern and see if numerically there even is hope for a finite solution. So again, this could be stronger, but in special cases, but I like to phrase it this way. And what one can show with that Lipschitz conditions that I showed you is that, that the expected value of the distance, the Wasserstein distance of order p, is bounded from above by this equation. And again, in the cases, and in most cases we can always find this, that this Lipschitz constant is strictly smaller than 1, this basically tells you that this is converging as fast as these distances on the right. But this notice that what I got rid of is the approximation. With the hat, I have this approximation of doing the bootstrap again and again and again. Without the hat, this is your standard sample pool of IID random variables. So now the question here is basically a question about just if you have the true distribution and I give you a sample of IID observations of the true, how quickly is it converging to that? So this sort of a law of large numbers kind of thing going on here, but no bootstrapping. In the special cases, when you actually can compute this, and there's a really nice couple of papers that have studied the Wasserstein distance and the moments of the Wasserstein distance between a sample of IID and the real. So that's, again, a whole area of research in this bootstrapping literature. Then there's really nice bounds that give you a polynomial rate here. So this comes from substituting the best possible rate for the expected Wasserstein distance between a pool of IID samples and the real distribution, and you get usually that it's polynomial decay with a power that is pretty ugly. When you don't have moments, this is a smaller term, and it can be very, very, very small. When you have finite variance and higher, this is your best possible case, which is the central limit theorem set, right? So the n to the m, in this case, to the -1/2. So this is the central limit case. This is the stable law or sort of power law case when you don't have finite variance. And unfortunately, that sort of sucks in practice, especially because many examples live here. But that's the best you can do. So I said, the theorem itself, you don't need this to be a contraction. When it's not, when it is, you get really nice accurate results. When it's not, what's interesting is, at least in my experience, if you can't find it, that means you can't find a solution. I mean, it really is like this HP is something that will pop up also in trying to show the existence of the solutions. And if you can't find it, that chances means that there won't be even a solution. And again, this is just a little note that what this means from the point of view of interpretation point of view is that if you look at the best rate at which the bootstrapping is getting close to the real thing that we're trying to approximate, it's of the same order of magnitude as the non-bootstrap version. So you're not losing anything by the bootstrapping in terms of the rate of convergence. So you actually are pretty much where you would have been had you actually done the IID thing. These are sort of other couple of questions people in simulation will surely talk about. One thing is convergence and probability. One thing is convergence almost surely. One gives you weak estimators. One gives you strong estimators. And this, to my surprise, I hadn't actually found anybody who had bothered even establish this. This is a little bit trickier to prove. Under the first set of conditions and twice the moments, it's a pretty bad, like you have a lot of moments. Some examples satisfy no problem, some of them don't. Then you can easily show that you have convergence almost surely using the same standard trick for the law of large numbers, which is basically once you have, you do kind of Chebyshev inequalities and with the fourth moment or the 2p moment, and sort of the same way that you would prove the strong law of large numbers, you can sort of argue for this case. But if you don't want to, again, when you see this kind of moments, you know that there's something wrong. You should not need much more than what you actually have to get those so strong laws. So if you want to get the best we were able to get without going too crazy as p plus delta moments, which is very close to the optimal. And again, in that case, what we use is the sample path Lipschitz conditions. And again, you have almost sure convergence of this. This is what I said before. The whole point is you want estimators. So you say that an estimator is weakly consistent if it converges in probability. It's strongly consistent if it converges almost surely. And as a straightforward corollary to those theorems that I showed you, under the first set of conditions, you get that the empirical average of a function h over your sample, remember, these are not independent, so you can't expect this upfront to satisfy anything, a law of large numbers, but they are coming from the algorithm. This is another way of writing it. This is a consistent estimator for the actual mean. Again, this is a consequence of the Wasserstein metric going to 0. And if you can argue the almost sure convergence of the Wasserstein metric, then it's a strong consistent, right? A strongly consistent estimator. So those are the kind of results that, that one wants to have in terms of knowing that what you're doing is accurate. In practice, even if you're not sure that a fixed point exists, at least you know that it's not because of the algorithm. The algorithm is working. So if your algorithm is giving you samples where things seem to be diverging, chances are they are diverging. So I guess that's another way of thinking that even in the cases where it doesn't exist, you still need to have that certainty that the errors in what you're seeing are not coming from the simulation itself, which is sort of a pitfall in simulation. Sometimes you don't know whether it's real or whether it's just an artifact of your method that you're using. So this answers that question, is the method is consistent even if the points don't exist. And the problem that I wanted to share with you today, which I think answering to Andrea's call for something that is worth publishing and not too hard, or not extremely hard, probably a week's worth of time if you're already sort of familiar with a lot of these things, is to actually get what you normally want in simulation, which is you want the point estimate that we did, and now you want the confidence interval, right? The confidence interval means you need some kind of central limit theorem to be able to provide that. And in reality, a simulation method that doesn't have confidence intervals is sort of useless. There are examples of methods that you can prove that it converges, but with the confidence interval is the entire line, what's the point, right? So this is what I consider to be an interesting open question that nobody has actually worked out yet. And my hint for you is that, again, let's look at the case where you can expect to have it. So ask for what in my mind is always having variance of the dp metric. So 2p moments. And just to make things simpler, why not a little epsilon more? That makes always the calculations a little bit more straightforward. And if you look at the estimator, here I'm looking at my empirical average here. And what I'm going to subtract here is the conditional mean of that empirical average, given the pool. So now these are IIDs. Because conditionally they are IIDs, it's not very hard to see that this guy satisfies a CLT. Now the question is, we don't want this, guys. We want this without the conditioning, right? Because that's the one that matters. We want to show that if I center this against the expected value of RK, then that satisfies a CLT so that I can construct the confidence intervals. So this is one step that I believe is a key element to actually showing that you have a full central limit theorem for the whole thing. And of course, there are some dependencies that need to be worked out there in the middle. If you are interested, I'll be happy to talk to you more about what I think is the path to do that. And what are the obvious first things to do as an exercise could be to make sure that you understand what it's doing. Again, this is easy, but worth publishing eventually. And just to give you one picture to remember of how these things work. This is the smoothing transform. I believe it's a binary tree. It was a fairly simple one, so it wasn't huge. And we did 10 generations, so this 10 refers to the K, so this is 10 generations of depth of the tree. This is 2 weeks worth of computation time. That after we did it, after we had the picture, so my student decided, let's just do it anyways. So this is our computed values. They're still not perfect. Again, this is sort of heavy. It's not optimal, but with 2 weeks, we got something that looks very nice. And then we did it again with this method with a pool of 200 and a pool of 1,000. So this is the M. M equals to 200. M is equal to 1,000. This is 1,000 independent copies of the entire tree for depth 10. As you can see, with 200, it runs in a blink of an eye. You'll get something that is still somewhat noisy, but at least it's getting there already. And if you give it 2.1 seconds, you're already in the red line, which is really, really good. So 2 weeks versus 2.1 seconds can easily make the M twice as much and still run under 5 seconds. And that's how big the efficiency gain is in this kind of thing. Which is why, it's not the hardest stuff to do once you get into the notation, but it is worth it. And surprisingly, it's something that people in computer science use, and just nobody had cared to prove that it actually works. Okay, that's, I think, all for today.
What is the importance of the P in your Stein metric?
The importance is, for example, if I want to do this with Quicksort and my default is, let's say, P equals 1, then Quicksort doesn't satisfy the contraction there. So putting it for...
When it satisfies or not? Or
yeah, so you want to find the P under which you can get that contraction so that it works, right? That's really, really what it is. The Lindley equation, for example, satisfies under the stability condition that is needed for the solution to exist, will satisfy that dp, expected value of dp is finite for all p. But Quicksort does it for all p too. But in particular, it starts with 2, I think. 2 and anything bigger than 2. Because the uniform, if you just compute the expected value of the uniform, you get 1 over 2, but you have 2 of those, so it's 1, and that's not contraction. It's not a strict contraction, so it doesn't work, so you have to go to 2 or higher powers to get the contraction there. And find, which is the discounted threesomes, I think works also for 2, but not for 1. So again, it's just, depending on the example, you want to be able to say that, to have the result for any p, the p that works.
Okay, but there are
some where 1p won't work, like smaller p's won't work and you have to go higher. Some where the small ones will work and the high ones won't. There's both examples going both directions. So this is just the most general way of making it useful, no matter what. Any other questions? You have coffee or
No,
no coffee?